In mathematics, 4-manifold is a 4-dimensional topological manifold. A smooth 4-manifold is a 4-manifold with a smooth structure in dimension 4, in marked contrast with lower dimensions. Topological and smooth manifolds are quite different. There exist some topological 4-manifolds which admit no smooth structure, and even if there exists a smooth structure, it need not be unique. 4-manifolds are of importance in physics because, in general relativity, space-time is modeled as a pseudo-Riemannian 4-manifold. Topological 4-manifolds. The homotopy type of a simply connected compact 4-manifold only depends on the intersection form on the middle-dimensional homology. A famous theorem of M. Friedman implies that the homeomorphism type of the manifold only depends on this intersection form, and on a Z2Z invariant called the Kirby-Sieben-Min invariant. And moreover that every combination of unimodular form and Kirby-Sieben-Min invariant can arise. Except that if the form is even, then the Kirby-Sieben-Min invariant must be the signature. 8. Examples. In the special case when the form is 0, this implies the 4-dimensional topological Poincare conjecture. If the form is E8, this gives a manifold called the E8 manifold, a manifold not homeomorphic to any simplicial complex. If the form is Z, there are two manifolds depending on the Kirby-Sieben-Min invariant. One is two-dimensional complex projective space, and the other is a fake projective space, with the same homotopy type but not homeomorphic. When the rank of the form is greater than about 28, the number of positive definite unimodular forms starts to increase extremely rapidly with the rank. So there are huge numbers of corresponding simply connected topological 4-manifolds. Friedman's classification can be extended to some cases when the fundamental group is not too complicated. For example, when it is Z, there is a classification similar to the one above using Hermitian forms over the group ring of Z. If the fundamental group is too large, then Friedman's techniques seem to fail and very little is known about such manifolds. For any finitely presented group, it is easy to construct a compact 4-manifold with it as its fundamental group. As there is no algorithm to tell whether two finitely presented groups are isomorphic, there is no algorithm to tell if two 4-manifolds have the same fundamental group. This is one reason why much of the work on 4-manifolds just considers the simply connected case. The general case of many problems is already known to be intractable. Smooth 4-manifolds. For manifolds of dimension at most 6, any piecewise linear structure can be smoothed in an essentially unique way. So in particular, the theory of 4-dimensional place manifolds is much the same as the theory of 4-dimensional smooth manifolds. A major open problem in the theory of smooth 4-manifolds is to classify the simply connected compact ones. As the topological ones are known, this breaks up into two parts. Which topological manifolds are smoothable? Classify the different smooth structures on a smoothable manifold. There is an almost complete answer to the first problem, of which simply connected compact 4-manifolds have smooth structures. First, the Kirby-Sieben-Min invariant must vanish. If the intersection form is definite, Donaldson's theorem gives a complete answer. There is a smooth structure if and only if the form is diagonalizable. If the form is indefinite and odd, there is a smooth structure. If the form is indefinite and even, we may as well assume that it is of non-positive signature by changing orientations if necessary. In which case, it is isomorphic to a sum of m copies of II1, 1 and 2 n copies of E8 for some m and n. If M3n, then there is a smooth structure, given by taking a connected sum of nk3 surfaces and m-3n copies of S2 times S2. If M2n, then for root proved that no smooth structure exists. This leaves a small gap between 10/8 and 11/8 where the answer is mostly unknown. The 11/8 conjecture states that smooth structures do not exist if the dimension is less than 11/8 times the signature. In contrast, very little is known about the second question of classifying the smooth structures on a smoothable four-manifold. In fact, there is not a single smoothable four-manifold where the answer is known. Donaldson showed that there are some simply connected compact four-manifolds, such as Dolgachov surfaces, with a countably infinite number of different smooth structures. There are an uncountable number of different smooth structures on R4, see exotic R4. Fintushel and Stern showed how to use surgery to construct large numbers of different smooth structures on many different manifolds, using Seiberg-Witten invariants to show that the smooth structures are different. Their results suggest that any classification of simply connected smooth four-manifolds will be very complicated. There are currently no plausible conjectures about what this classification might look like. Special phenomena in four dimensions. There are several fundamental theorems about manifolds that can be proved by low-dimensional methods in dimensions at most 3, and by completely different high-dimensional methods in dimension at least 5, but which are false in dimension 4. Here are some examples. In dimensions other than 4, the Kirby-Siebenmann invariant provides the obstruction to the existence of a place structure. In other words, a compact topological manifold has a place structure if and only if its Kirby-Siebenmann invariant in H4 vanishes. In dimension 3 and lower, every topological manifold admits an essentially unique place structure. In dimension 4 there are many examples with vanishing Kirby-Siebenmann invariant, but no place structure. In any dimension other than 4, a compact topological manifold has only a finite number of essentially distinct place or smooth structures. In dimension 4, compact manifolds can have a countable infinite number of non-diffeomorphic smooth structures. 4 is the only dimension n for which Rn can have an exotic smooth structure. Our 4 has an uncountable number of exotic smooth structures, see exotic R4. The solution to the smooth Poincare conjecture is known in all dimensions other than 4. The Poincare conjecture for place manifolds has been proved for all dimensions other than 4, but it is not known whether it is true in 4 dimensions. The smooth H-cobordism theorem holds for cobordisms provided that neither the cobordism nor its boundary has dimension 4. It can fail if the boundary of the cobordism has dimension 4. If the cobordism has dimension 4, then it is unknown whether the H-cobordism theorem holds. A topological manifold of dimension not equal to 4 has a handle-body decomposition. Manifolds of dimension 4 have a handle-body decomposition if and only if they are smoothable. There are compact four-dimensional topological manifolds that are not homeomorphic to any simplicial complex. In dimension at least 5, the existence of topological manifolds not homeomorphic to a simplicial complex was an open problem. In 2013, Cyprian Manolescu posted a preprint on the arXiv showing that there are manifolds in each dimension greater than or equal to 5 that are not homeomorphic to a simplicial complex. Failure of the Whitney trick in dimension 4. According to Frank Quinn, two n-dimensional submanifolds of a manifold of dimension 2n will usually intersect themselves and each other in isolated points. The Whitney trick uses an isotopy across an embedded 2-disk to simplify these intersections. Roughly speaking, this reduces the study of n-dimensional embeddings to embeddings of 2 disks. But this not a reduction when the embedding is 4. The 2 disks themselves are middle-dimensional, so trying to embed them encounters exactly the same problems they are supposed to solve.